Next up, we have Curtis Lassam, who will be talking to us about hash functions and us, Partners in Freedom.
Hello, everyone. I'm Curtis Lassam. That's C. Lassam on Twitter. I work at Sauce Labs, and we are going to talk about hash functions. So I'm going to do my best to show you why this fundamental technique belongs in your toolkit. And you can tell from my drawing of a toolkit, I am not a handy man. So we're going to talk about hash functions, hash tables, Bloom filters, choosing hash functions for your data structures, and hashes in security. So let's get started with what is a hash function, the very beginning. Here's an example. Let's write a function that takes a string, splits it into characters, converts every character into an integer, adds the integers together, and mods the result by 100. This is a hash function. Not every hash function works this way, but this, like many other functions, is an example of a hash function. It has a number of useful properties. Regardless of what sequence of characters you put in, you're guaranteed that the output will always be between 0 and 99. The output for a string will always be the same. And many different inputs can produce the same output. Also, given the output, it's impossible to guess the input that produced it. So I know that invoking the Wikipedia definition of something is the presentation equivalent to opening with Webster's dictionary defines, but the Wikipedia actually has a good definition of a hash function. A hash function is any algorithm that maps data of arbitrary length to data of a fixed length. So no matter what sort of data you put in, you always get a variable within a certain range. So that's a hash function. Now let's talk about hash tables. Hash tables are a data structure concept used to store keys and values. Keys and values are important. You deal with them when you work with things like MongoDB or Memcached or Python dict. And if you're dealing with keys and values, chances are behind the scenes something clever with hash tables is happening. It could be something else, like a tree or a trie, but we're not talking about those right now, so I'm going to pretend that they don't exist. So let's start with a big block of memory, let's say an array with 100 elements. We want to store the value hash 215D29 against the key color. So we run a hash function on the key, color. This produces a number, which we mod by the length of our table, and this gives us an index. And then we can store our value at the location pointed to by the index. That's a hash table. Easy peasy. But it is not quite so easy nor quite so peasy. As the array fills up with values, it gets more and more likely that we'll have a hash value point to a spot in the array that's already full. This is called a collision, as you might imagine. What do we do when there's already a value in the spot where we want to store a value? We can keep walking forward in the table until we find an available spot. This is called linear probing. Alternatively, we could root a linked list at every space in the array. That way, our hash table can take as many values as we can throw at it. Or a tree. We could also root a tree at every space in the table. This, rooting a separate data structure at every spot in the table, is called a chained hash table. There's one problem with a chained hash table. Here there's a bunch of different values stored where we're looking for the key, cheese. How do we know which is the right one? We need to store the key with the value in the second data structure so that we can make sure that we're retrieving the right thing. This is going to be the case anytime we have to deal with collision. If we can retrieve multiple potential values from our hash table, we need to be able to tell which is the correct value. So even with some strategy for collision detection in place, it's possible for the table to get so full that it performs very sluggishly. A crowded chained hash table is only a little bit better than a linked list. Or in the case of hashing strategies that just shuffle addresses around, it's possible for the table to become completely full. When this happens, it's time to rebuild the hash. This is the time-consuming process of addressing an even bigger whack of memory, taking all of the keys out of the array, rehashing them, and putting them in the second array. There's one language I can think of whose default hash table implementation can perform this computationally intensive step unexpectedly anytime an insert pushes the table above a predefined load limit. But for the sake of politeness, I'm not going to mention which language. Of course, linear probing and chained hashing are not the only hash table management strategies. There are many, many ways to manage a hash table. Like Robin Hood hashing, which steals data from your richer tables and inserts it into your poorer tables, or hopscotch hashing, where you implement the entire array in chalk on the pavement. You probably shouldn't fact check me on those last two. So a hash table is a data structure that uses the result of a hash function as the location to store the data in memory. Insert happens in constant time. Delete happens in constant time. Lookup happens in constant time. And you shouldn't linear search through a hash table. So that first few minutes of the presentation was there to get you up to speed on the basics. Now let's get to some of the meat of the presentation. Bloom filters. Bloom filters are fun. A bloom filter is a great way to keep balloons out of your face. A bloom filter is a data structure that's fast and space efficient, used to test for membership in a set. That's important. It tests for set membership. It doesn't store any data. It can tell you if something is in a set, but you can't retrieve an item from the set. Like if we have 3 objects, banana, apple, and bowling ball, and a bloom filter representing the set of fruit, we can use the set to determine that banana and apple are probably fruit, and that bowling ball is definitely not. But we can't give you a list of all the fruit that were used to populate the set. We don't know them. So a lot of the time, bloom filters are used to answer questions like, is chumpies a real word? No, chumpies is not a real word. Is evil.ru a malicious website? I don't know, I've never been there. And is main.css in the cache? Yes, it is. Is this a banned image? So let's look at the problem of banned images a little bit. Let's imagine we're running a forum, and our itinerant users keep posting banned images. How do we know, looking at image data, if an image has been banned? Let's say we run a hash function on the image. You can hash images, you can hash just about anything that's data, mod the result by the length of an array, move to that index location in the array, and save a link to the image there. Then when we're checking a new image, we can hash it and see if it's in our array. Of course, this is just a bog standard hash table, and I'm supposed to be talking about bloom filters. This works fine, the strategy I've used so far, but it takes up a lot of space, and I promised you space efficiency. Let's imagine there are 5,000 images we want to keep out of our forums, and they take up 100 kilobytes each. That means about a 500 megabyte table of duplicate images. While it's not a ton of space, it's enough that you probably won't want to keep that in RAM or send it to a client. Remember, though, we don't need storage from our data structure. We're really only interested in whether or not this image exists in our data structure. So let's imagine we store zeros in every space in our table, and we store ones where the hash functions land. That way, we can check if an image is banned by hashing it, modding it, and then checking if that spot in the array has a 1 in it. If there's no 1 there, we can't possibly have seen that image before. There's only one slight problem with this technique. What happens when we have a different image that accidentally collides with an image that we set earlier? This creates a false positive and unfairly takes pictures of Nicolas Cage out of circulation. So how do we stop collisions like this from occurring? Well, we could use a hash function that guarantees an astronomically low probability of collision. MD5, for example. It's a hash function that guarantees an astronomically low probability of collision. But with the astronomically low probability of collision, you get, axiomatically, an astronomically high number of potential outputs. With 1 bit for every output, you're suddenly saddled with 4 times 10 to the 25 terabytes in your array, which is also a little bit unrealistic to cram into your RAM. But it does hit on one of the 2 strategies we could use to reduce collisions in our bit array: more space. Now let's look at the less obvious strategy for reducing collisions: more hash functions. Instead of hashing our image just once, let's hash it twice with 2 different hash functions. This gives us 2 different locations in the table, and we can store a 1 at both of them. Another image might share the result of one of the hash functions, but it's not as likely to share the result of all of them. And if any of the hash functions point to a location with a 0 in it, we know that this object can never have been entered into the bloom filter. So this is a bloom filter, a bit field and multiple hash functions to set the bits in that field. We put items in by hashing them multiple times and setting the bits at all of those locations, and we check if items are in the set by hashing items multiple times and checking if the bits are set at all of those locations. There are some downsides to this. Because each item we put into the bloom filter has multiple hash functions, there can be some overlap, which means we can never delete anything from the bloom filter. If we do, we run the risk of accidentally deleting something else from the filter. On top of that, we've reduced the chance of collision But it's impractical to reduce that chance to effectively 0. So there's always some chance of a false positive. However, the probability of a false positive is a number that we have some control over. If we know the desired probability of a collision, in the case of our image filter, let's say 0.1%, and the number of things that we want to put in the filter, we mentioned before, 5,000 images, we can use hand-wavy math to determine how much space we need and how many hash functions we need to get an optimal solution. Waving my hands. You don't actually have to memorize this math or write it down. It's really easy to find on the internet. And so doing this math with our numbers, we need an array of 71,888 bits, which is 8.8 kilobytes. And that's small enough that we could keep it in RAM. We could send that Bloom filter to the client side if we wanted to. It's certainly easier to work with than 500 megabytes of images. And we need 10 different hash functions. That is to say, the optimal packing requires that each item we place in the table set 10 different bits in the Bloom filter. A lot of the time, Bloom filters are paired up with other data structures that handle the actual storage of the items. For example, they're super useful when paired with data structures that exhibit worst-case performance when searching for items that are not in the data structure. In a linked list or unsorted large array, for example, you get the worst possible case when you're searching for an item that just isn't there. The Bloom filter can check before you hit the data structure if the data is in the data structure. They're also very useful when the retrieval step for data takes a long time. For example, when a network call needs to be made to a faraway database. A local Bloom filter is a wonderfully fast way to know if you're wasting everybody's time with a request for data that just doesn't exist. Or data with a very low hit rate. If you're dealing with the sort of data where you're getting 10 misses for every hit, is this a malicious website, for example, you can catch all of these misses with a Bloom filter. So in summary, and this is a very small summary for the people in the back, so I'll try to be loud, Bloom filters are fast, compressed, storage-free data structure used to check for set membership. It's implemented as a set of hash functions pointing to a bit array. No retrieval is allowed, and no removal is allowed. So now let's talk about how to pick which hash functions to use when you're building data structures. I mean, I showed you my awesome cheese hash function earlier, but it's terrible, and on top of that, it really only works on strings. Now, the number of different hash functions are countless. Each one is a unique snowflake. Only 3 of the ones on this board are made up. And if you can pick them out, I might get a chance to ask you which ones they are at the end of the presentation. And I'll come back to that slide if we need to. So which ones do we pick for our data structures? Well, for data structures, the properties we're looking for are that the hash function should be fast and it should be well distributed. When we say fast, what we mean is non-cryptographic. Cryptographic hashes are awesome. They have a bunch of properties that make them totally badass for security functionality. The most important one being that they're collision resistant. It's astronomically unlikely that you'll ever be able to find 2 different items that hash to the same hash value. But these cryptographic features also make them a bit more processor hungry. So we should avoid hashes like SHA or MD5 when we're working on data structure stuff, because we don't need awesome security features in our Bloom filter. It's just a waste of CPU cycles. So non-cryptographic. And well distributed, which means that no matter how similar your data is going into the data structure, the output should appear all over the spectrum. Hash functions that exhibit this quality are known as avalanching hashes, because small changes in the input lead to large changes in the output. Of course, this is also a desirable property in cryptographic hashes, but this one we're willing to blow our precious processor time on because it's really important for data structures that depend on hash functions to have well-distributed hash functions. A common hash used for this purpose is the non-cryptographic, well-avalanching public domain Murmur3, implementations of which exist for most modern languages, including Python, and which has appeared in numerous open source products, including Hadoop, Cassandra, and Nginx. It also takes a seed value, so you can create dozens of different hash functions out of the Murmur3 base hash function, just by changing the seed value. There are some reasons, though, that you might actually want cryptographic hashes in your data structures. A clever attacker, for example, might take advantage of your data structure and only insert data that matches a certain small set of hashes, forcing collision after collision until your whole application falls over. It's been demonstrated that Python is vulnerable to this sort of attack, although the BDFL called this some security researchers drumming up business. In PEP 456, Christian Himes lays out the reasoning behind choosing a cryptographic hash function as the default hash function for Python strings and bytes, comparing the cryptographic SIP hash with the non-cryptographic murmur hash, as well as the previous CPython hash implementation. This PEP was accepted, and as of Python 3.4, the default hash function for strings and bytes is SIP hash. One other thing, we hashed an image to put in our data structure earlier. What sort of hash function works on an image? Well, most of them really, but a perceptual hash, or p-hash, is designed specifically to cluster very similar images together in the hash output. For example, if it's the same image but sized larger or skewed to the left, it should end up with a hash function very close to the original image. Of course, by nature, this hash function won't be distributed in the way that we would need for an optimal general-purpose data structure. It's the opposite of an avalanching hash. Small changes in the output lead to almost no changes in the output. I said output twice in that last sentence. Pay no attention. But we can abuse that property so that false positives are unfairly clustered on images that look very similar to our banned images, which would actually probably be a good thing in the case of trying to find banned images. So that concludes the data structures portion of the talk. Now let's talk about how hash functions contribute to the security of your application. So you're running a web application, and the worst case scenario happens. Some hacker makes off with the user table from your database. How? I don't know. For the sake of argument, let's say SQL injection. At this point, your users are all shit out of luck, right? I mean, some brigand has made off with all of their passwords. Oh, well, no, because our developers have cleverly obscured the passwords before saving them. Hopefully, you're all already aware of this technique. In order to hide the passwords this way, when the user creates a password, we don't save the password itself. Instead, we save the result of a hash function. Later, when the user tries to log in, they provide a password. We hash the password and compare it with our hashed password for the user. If the two match, the user has provided the correct password. Of course, if the two different passwords ever collide, if two strings hash to the same output value, then it would be possible to log in to our site with the wrong password. That's bad. Do you remember earlier when I said that cryptographic hashes like MD5, for example, have a feature called collision resistance, which means that two inputs are astronomically unlikely to collide? Here is where that is super important. Now our passwords are protected. Yep, totally protected. Nothing could possibly go wrong. Okay, so let's talk about dictionary attacks, the way to break hashed passwords. So we've stolen a whole database full of usernames and hashed passwords, and we want to get at the raw passwords so that we can try them out on banking sites and stuff. So what we can do is create a list of everything that we can think of as a possible password, an enormous comprehensive list of passwords. Then we use the same hash that the programmer used to hash the original password, and we run that on every single item in our gigantic password list. Now we have a giant collection of hash-to-password pairs which we can compare against the original data. Anytime we find a match with one of the hashes in our set, we know what the password must have been. This checking of every hash in the set against every hash in the database is n squared, but it's inherently very parallelizable. So with a bit of optimization, this can run very, very fast. And in fact, some people have managed to use graphics hardware to run hash functions very, very, very quickly. So this is called a pre-computed dictionary attack. It's important to note that this isn't a rainbow table. A rainbow table is a different thing, involving hash chains that accomplishes the same task but using a lot less storage space. And I'm not going to describe them today because I'm not sure if I have enough time and I don't understand them super well. So the MD5 hash function is so common that Juuso Salonen, and I really hope I pronounced his name right, released a utility called BozoCrack that works by taking a hashed password, searching for it on Google, and then MD5 hashing everything that comes back in the Google search results until it finds a match. It's not as comprehensive as an MD5 dictionary, but it still manages to be depressingly effective, like 80% effective. It's really scary. So part of the reason these attacks are so effective is because every user's password has been hashed with the same hash function. It's possible for us to test passwords against the entire table all at once. While it's unlikely that we'll ever crack all of the passwords, we're able to suss out the users who have simple passwords very, very easily. Just testing the whole database against the 1,000 most common passwords shouldn't take more than an hour, and will provide us with a wealth of potentially useful data. So what we want to do to reduce the effectiveness of this kind of attack is to use a different hash function for every single person in the database. This doesn't mean we need to enlist thousands of different hash implementations. What it actually means is that we want to use one hash function that we seed with a different value for each user in the table before we hash the password for that user. It has to be a value that we have access to, because we need to be able to recreate this custom hash function every time we check the user's password. It's quite common to use the username for this value. Doesn't mean you should use the username. Cryptographers recommend that you create a large block of randomized data and save it against the user to use as a seed. This hash seeding value is called a salt. So a salt is random data used as additional input to a hash function to protect against rainbow table and dictionary style attacks. Okay, so that covers the very, very basics. And when I say basics, I mean the very most basics. This isn't exactly state of the art. Unix's crypt function first used salted hashes to protect against dictionary attacks in 1976, a full decade before I was born. So now let's talk about not using MD5, which is an important topic in hashes all to itself. MD5 is well known and well understood, and it's been in use for a very long time. Unfortunately, in that very long time, some cracks have begun to show in this venerable hashing algorithm. The biggest reason to avoid MD5 is simply that it is too fast. It's possible to MD5 hash millions of values per second. This makes brute force attacks against MD5 hashed passwords very, very easy. This MD5 hashing Python script I wrote runs, on a cheap little virtual machine, 1 million MD5 hashes in 1.5 seconds. And this is just like a Vagrant 512, pop-up virtual machine on my computer. It's not really something that is beefy. With a much faster computer, you can run many more hashes much more quickly. So instead of MD5, I recommend bcrypt or scrypt or pbkdf2. Now, bcrypt is designed to be slow. Using the default setting on the same virtual machine, this run, where I use bcrypt instead of MD5, would take me 3.4 days. The last one was 1.5 seconds. This one took me 3.4 days. This, combined with Assault for each individual user, means that brute forcing passwords out of a database could take days or months per user rather than an hour or two for the whole thing. bcrypt also comes with a work variable that you can crank up to 11 to make things even slower as hardware gets faster. When I turn it up to 15, my million hash script goes from 3.4 days to run to 26 days to run. I didn't actually let it run for 26 days. I actually just let it run for a much smaller amount of days and multiplied the time. So at this point, logging a single user into my site could take a couple of seconds. So I'm not sure if they're willing to wait that long. But it's nice to have that work variable there that I can crank up as computers get faster. So for password security, you should be using something that's specifically designed for password security, like bcrypt or pbkdf2. But even for general purposes, if you're looking for a secure hash algorithm, MD5 is kind of old and broken. It's actually been shown that you can cause force collisions in MD5 by researchers, mind you, but it's a thing that can happen. So instead, try secure hash algorithm. So secure hash algorithm, or SHA-5112, has become a new standard for hashing, one that's cryptographically much more secure. And that's been hash functions, hash tables, Bloom filters, choosing hash functions, and hashes in security, which concludes the body of the presentation. Now, I believe that leaves us a little bit of time for Q&A. Before we start Q&A, though, I'm going to bring up my list of fake hash functions, and I'm going to see if you can guess which ones are the fakes. No, it's not that one. Sum41 was a fake hash function. Come on, hash function slide. I know you're in here somewhere. Oh, it was in data structures. It wasn't in security. That's why. Here we go. OK, so we've successfully identified Sum41 as a fake hash. The Lester B. Pearson hash is a fake hash. The Pearson hash is a real hash, though. Let's see here. MD5 is real. Any more guesses? The perfect hash is a real hash. The perfect hash is a hash function that has been it's been calculated in advance so that the set of inputs you have perfectly map to a set of outputs. It's a really interesting hash. The fake hash here is the country hash. City hash is real, country hash is fake. Pearson hash is real, Lester B. Pearson hash is fake. Sum 32 is real, Sum 41 is a band. So having concluded that, if you have any questions, now would be the time to ask them.
Thank you very much. And just a reminder to please ask a question and try to be concise. Thanks.
Just a quick question. Is there a good Bloom filter implementation for Python on PyPy or something?
I've looked around. I remember looking and eventually creating my own, but I'm sure there's one already in Python somewhere. I mean, it's a really common data structure, and it must exist already. And I think the reason I created one was just because I wanted to do research for this presentation. So.
Okay, thank you.
That's all the questions.
Thank you very much.
Thanks, everyone.